Hello everyone, this is Nargis from University of Klagenfurt. Today I would like to present our recent accepted paper in the distributed machine learning for the Intelligent Computing Continuum workshop, which was held on 4th of December in conjunction with the UCC conference 2023 in Italy. The work is about the comparison of the microservice call rate predictions for replication in the cloud. This work was a collaboration with Arman from Azad University in Iran, Petram, previous master student in Klagenfurt and currently PhD student in Paris Tech, and Nicola and Dimitrov from a Sintef company in Norwegian Institute, and also University of Oslo, and Ahmed from Oslo Met University, and Rado as my supervisor at University of Klagenfurt. Firstly, I will introduce the topic of this work, and I will present the main motivation behind the work. Then I will proceed with the models related to the data processing and machine learning predictions. Then I will present the architecture, design, the experimental design, analysis, and the result, and then I will conclude this presentation. The recent shift towards the increasing number of microservice-based applications to be executed and processed in the cloud-native infrastructure has brought new challenges in terms of the scheduling, deployment, and orchestration on the computing devices. These challenges are in terms of the scaling out the microservices, or it's better to say in terms of the technology, the distributed technology, the containerized microservices, responds to the high load and increasing load that is coming from the users who have submitted their applications to the cloud. From one side, we have these applications, and from the other side, there are the cloud providers who are providing the virtual machines or the other type of services, the other types of services provided throughout their infrastructure. As an instance, Alibaba Cloud, founded in 2009, from that moment on, they have different branches all over the world in different regions, and they provide reliable and secure cloud computing and data processing, I would say, services. Also, just for your information, in 2017, they have been the partner of the Olympic Games. Previously, we published a paper in the proceeding of the IEEE Cluster Conference, which was held in Heidelberg, Germany in 2022. However, this work did not consider, and it doesn't expect, in this work we did not inspect the scalability requirement of the microservices. Mainly the work was about the scheduling based on the matching in principles for matching the microservices to the computing devices based on the specific parameters such as the data processing and queuing time and the data transmission time. However, this work did not explore the prediction models by considering the different request arrival rate from the end users. Therefore, we started to investigate the related work in regards to the scalability methods that are presented for the cloud computing environment. These works mainly focus on the resource and application processing metrics. And I would say they rarely considered predicting the stochastic changes in the user's requirements, such as the dynamic request rates. From the other side, these methods are mainly using those type of machine learning models, such as the deep learning or deep reinforcement learning. However, recently there has been a paper published that it shows the performance of the tree-based machine learning models, such as, for example, the boosting. As a specific example, the gradient boosting tree, which is really suitable for the tabular data, which in our case also exists. Please let me bring an example over the problem and also the solution that we presented in this paper. Let's assume that we have 3 different microservices. They are independent microservices. So there is microservice M0, M1, and M2 running on the resources 0, 1, and T. Each one of these microservices, while running on these resources, has the time of 0.7, 1.5, and 2 seconds per call, which is coming as a request from the user who has submitted the microservices. So from the other side, assuming that per second, each one of these microservices may receive different number of calls. For example, as you can see in the last column of the table, respectively 2, 2, 3, different number of calls per second. So considering a timeline from the start of the microservices to be executed until, for example, the 2 seconds, then each one of these microservices may not have still reached to the different number of calls that they have received. So the request may not have been satisfied. For example, M0 has just finished the 3rd call, so still the last call is remained. Therefore, to reduce this infrastructure bottleneck, in our paper, we proposed a solution that is based on the function, which is the multiplication of the call rate and the microservice time. So that, for example, for microservice 0, if we replicate it to 2, then probably it can satisfy the user's requirements in terms of the different number of calls that are being set. To start the solution, firstly, we model the data processing. So data processing streams consist of the producers. These producers are generating data that require microservices to execute them. Microservices are represented as the independent task. Also, the data flow is streaming from a producer and it will reach to a microservice. Each one of these microservices requires a specific amount of resources in terms of the CPU and memory, and also that the user may put some specific deadline also. So for that also we define a parameter. From the other side, I mean, this is the microservice and application side. So how about the resource provider side? So the resource provider provides some virtual machines, some cloud virtual machines, while each one of them has a specific capability, again, in terms of the processing and memory. So based on the utilization, then these machines can be presented to the users. There will be a matching or mapping between the microservices and the resources in the cloud. Each one of these microservices which are executed, they may have some specific time, as is observed in the previous slide, which is in terms of mathematical model, we define it as a ratio between the workload or processing workload over the processing speed of the device. So processing workload, which is the required workload of the application to be executed, and then the speed of that specific virtual machine as the capacity and the utilization which is available. The main objective that we estimate here is the number of replicas for horizontal scaling as a multiplication of the call rate and time. The machine learning models, as you're aware, are categorized into two different branches, the classification branches and the regression branches. The classification model predicts the class membership of an input, while the regression model predicts the value of a dependent variable based on the input that it received. Here we explore two different regression models, such as the linear regression, which fits a linear relation between the input, here in our case the microservice time, and the output, which is the call. To compare the performance of a strong neural network-based model, such as the multi-layer perceptron, we define it in two different layers as the input and output and the hidden layer. But in our case, the hidden layer consists of just two neurons, which could help us to really model it and to have a linear relation between the input and output, so that it would be comparable and also the complexity would get decreased, and the time also, the training time. From the tree-based ML models, the gradient boosting was selected, which estimates and constructs an additive model. As you can observe in this figure, as we go ahead through the iterations of the training, it will add more number of trees to the model, and also it will learn from its previous stage, which helps to create a more accurate model as it goes ahead. Having this processing model and DML model, we propose this architecture integrated with the other tools in the data cloud project. Here we assume that we analyze the microservice requirement, then we add it to the trace of the microservice that is available. Then we extract the feature sets for the inputs of the ML model, and the ML model we have here first. We try to fine-tune its parameters, and then we get the trained model, and then we pass it to the next module, which is one of the main module, or it's better to say the main goal, to predict or estimate the number of replicas of the microservices. Then after the predicting, and scheduling module is running, which helps really to create some schedules for different microservices to be executed over the cloud machines. For that, we rely on another tool in the data cloud project, which is the pipe, in which they have designed their orchestration systems so that it will use the scheduling plan that we designed here. The other tools that were integrated were the definition of the pipeline and simulation of the pipeline. Respectively, definition defines the pipeline based on the requirement of the users, and this is one of the main factors that exist in the design design bundle of the pipeline or application in the data cloud. The other tool is the simulation, which provides some simulation data while the execution of a large number of data pipelines or applications are required in terms of, the large amount of processing and memory. So it helps to get a better scheduling decision at the end. For the experiments and for the analysis of the models, we used the Python APIs, such as the scikit-learn and PyTorch, to implement the ML models. Basically, the GBR or gradient boosting model and linear regression were implemented in scikit-learn. We used the scikit-learn library of those modules, and MLP was implemented through the PyTorch API. Compare the performance of the algorithms on two different machines in terms of the training time and also the accuracy, the accuracy of the model or the errors. One of them was the virtual machine running on the Google Code Laboratory. It was GPU enabled and it had up to 16 gigabytes of memory. The other device was a personal device. It had 8 core and up to 16 gigabytes of memory. Another part of the experimental design was the workflow in that, which was from a trace from the Alibaba cloud. Of course, it was not just one trace, but multiple traces that we combined the rows or the records of them. This was the microservice trace, in which we could observe different types of the communication between the microservices, specifically to stateless microservices, as you can observe in this figure. So, for example, these two microservices or stateless microservices are interconnected to each other throughout the message queue, which is roughly 23% of all the microservice communications existing in this tool. We polished the dataset that we fed into DML models, and it's available in the Zenodo repository for your consideration. Overall, the main trace has roughly about the 1,300 different microservices containerized. And then, as you can see, as an example of a record, each microservice has a specific name, and there may be, for example, same microservices, but the containers ID are different, so they have been containerized multiple times. And then the metric that inside this trace is available is a response time, for example, and also the communication medium is also available. So in this case is RPC, in which throughout the whole data set it can be around 76%. And also the value. So the value helps us to create our feature sets. Mainly the time was between this range, 0.01 millisecond per call up to around 6,000 milliseconds per call. The call rate, the microservice call rate, had a range between 0.025 calls per second up to roughly 5,000 calls per second. Talking about the feature set, the time and the rate, we observed that the correlation between these features are about 75%, which helped us to have a better motivation to start to apply the ML model. DML models, as I said, LR, MLP, and GBR. LR showed a linear model. We tried to fit a linear model between the input and output. And also, as I said, by designing the MLP model based on 2 neurons in the hidden layer, we also reached almost a linear fit between the feature sets, I mean the input and the output here, which is the test data and the test data. And the GBR showed an almost non-linear fitting. Talking about the accuracy, the error, the loss of the model, and also the training time. So the training time of the linear regression model was lower than the other models, while the error rate of the linear regression was higher than the others. For the MLP, although the error, I mean the mean absolute error, is in the middle, also the mean absolute percentage error, which is the average of mean absolute error over the number of observations, and the error is, I mean the MAE is almost in the middle, while training time is higher because of the structure of the neural network, which ends up in this higher training time. However, the GBR has reached a lower error, while also we used the train model, as I showed in the architecture, to predict the number of replicas. To check the error that we reached throughout this prediction, MIP showed that GBR has reached to a lower error in comparison to the other 2 ML models. Okay, in this presentation, I presented the introduction for starting this work, the main motivation for replica prediction. I presented the description of the ML models, the 3 base ML models that we applied over the Alibaba dataset, which showed that the GBR gradient boosting model estimates the number of replicas close to the actual data for each microservice. In the future, we plan to explore and investigate the integration of these ML models that we developed through this work in the Kubernetes as the auto-scaling component of the orchestration system. At the end, I would like to attract your attention to the paper that is available also in the Zenodo repository. Of the code repository of the so please, at this level, let me show you the code repository of the implementation of the paper. So going to the cluster prediction repository, here you can see 3 different folders. This folder, which is related to microservice prediction. The resource prediction is an old project that we're developing. So coming to the microservice predictions, there is this file, which is a Python notebook, GBR, microservice call rate. And as you observe at the beginning, connecting to the Google Colab, loading the data set from that, and then starting with the NumPy and Pandas library to read the data set and then to extract the specific columns for the input and the output. And specifically, we use the train test split library API from the model selection API of the scikit-learn to split the data set. And also, we use the gradient boosting regression from the ensemble library of scikit-learn by considering the model fitting as is here for your observation. Then we fit the model, we fit the model into the data, and then we predict based on the testing data set. We calculated the MAP and MAE through the functions that are available from the scikit-learn matrix API. And then we plot the fitting of the model. And also for your information, we have presented the way that we have validated the model and whether it converges to an optimal result or to a close optimal result or not. Also, I would like to attract your attention to the other models that are available in the repository as well, and also the comparison of the models. Okay, thank you for your attention. Bye.